So to continue yesterday's discussion, what we were talking about is waves, right? And just for the clarity's sake, waves are energy. More importantly, waves are the translation of energy due to the vibration of a medium, but what it really means is that waves are the movement of energy, right? And so I've added some words there to help you remember. Translation is the same as propagation, is the same as movement. These are all terms used for describing waves and how energy moves. Translation is moving over distances while transforming. Propagation is the continued chain reaction of energy propagating through a system, which all equals movement, right? All of those things are interchangeable. But the definitions of the two particular types of waves are transverse and longitudinal, and they are based on the vibration compared to the direction of propagation. In other words, the direction in which the energy is moving. I showed you yesterday with the things hung from the ceiling. The pendulum swings horizontally even though the forces are up and down. The mass bouncing on the spring moves up and down while the forces are up and down. In one case, the forces are perpendicular to the direction of the energy moving, and in the other case, the forces are parallel to the direction of the energy moving. That is the difference between the two types of waves. So transverse is the first type of wave. This is when the vibration is perpendicular to the propagation. Right, so if you all take a moment and look at the spring here on the table between Riley and I. Yes, take time out. It's not a lot to write down, you get to it, right? Transverse waves, if the energy is going to move from me to Riley, the vibration is going to be perpendicular to that, right? So the direction of propagation is the direction the energy moves. This is this direction, yes? After it hits Riley, which is going to happen since she's holding the end of the spring stationary, it's going to bounce off of Riley and travel back towards me. In order to describe a transverse wave, we need the vibration of the spring to be perpendicular to the direction of travel, right? So perpendicular means 90 degrees. There's actually a few different possibilities, right? But if I turn this sideways, right, and we see an energy pulse that moves down the table from me to her. Don't be tempted, I'll let you play in just a second. Right? Does that make sense? Transverse is going to be perpendicular to the direction of propagation, right? And so the example is an ocean wave, which is more like a vertical wave, which would look more like this. Right? Which is exactly what an ocean wave looks like. It rolls off the ocean, crashes on the beach. What we are seeing here is an incomplete wave pulse because of the table, right? The table is preventing the spring from vibrating below where I'm inputting the wave. So it's actually adding friction, which is reducing the amplitude as the wave travels from me to her, which is why it decreases and eventually disappears.
I thought this table was like...
But it's just the fact that the table's here.
Yeah, I mean, it's literally because this is vibrating up and then trying to vibrate down, and because it hits the table, it stops vibrating. Whereas up here, right, if you look up, right, the energy keeps going, propagates back and forth for a much longer time frame, right?
What did you do with your hand the second time you did this? Sorry, I just
So, in terms of perpendicular, I'm either thinking about it being this way or this way, which is either one perpendicular. So I can go this way and make a wave like that, or I can go this way.
Why is that one?
When you're like looking at
Because the direction of propagation is still this way, and 90 degrees to that is straight up and down. So that is still perpendicular to the direction of propagation. It's just that there's more than one possibility. Propagation is translation or the movement of the energy, right? So it is the fact that the wave is moving towards Riley from me, right? Does that make sense? So when I go like this, right, you can clearly see the wave is going that way, but the spring is moving up and down. This is 90 degrees to the direction of propagation. So same thing horizontally, right? When I move this way, the wave is moving that way, but the spring is vibrating that way. So that is a different 90-degree possibility. So what you can imagine, right? Well, so the examples, there are two examples, which is the ocean, right? And you can imagine that the ocean waves look exactly like this. Large crests of water moving, energy moving laterally or horizontally along the ocean, right? Which would look very much like what you see in the wave pulse picture there on the board, right? Light is also a transverse wave, and so that actually brings in the fact that it can be transverse in any plane that is perpendicular to Riley and I, right? So rather than just horizontally or just vertically, I could also go diagonally like this, right?
Really?
Because that would still be perpendicular to the direction of propagation. So there's actually a 360-degree circle, right? That no matter which way I'm going, I'm always perpendicular to going that way. So what that means is that light coming out of the lights above us, that it's really hard to tell which direction the light is actually rotating, because we can't actually see this happening. What is interesting is that if light reflects off of a mirror or something flat like a calm surface of water, right, a really nice smooth reflective surface, once the light reflects off of the water, then the orientation is exactly the vertical like this.
Right,
So that's exactly how polarized lenses work, right? You've seen polarized sunglasses before. Polarized sunglasses block the orientation of a wave if it's a very specific orientation. And so if it reflects off of water, right, your polarized sunglasses will reduce that glare, because that glare has a very specific orientation, but you can still see through the sunglasses because there's a number of other light rays that are all oriented in different directions.
What if we like held it up in the air
Yes?
and then you?
So the reason why that doesn't work, right, is because I have the tension very low so that we can have a nice, low, slow wave, right? We can do the same thing up here with this one, right? If I go diagonally, right, I still get a wave pulse that travels laterally along the spring. So you can imagine that I can go in any direction and pull this way or down, right? 360-degree direction, and the energy will still propagate this way. That is much more indicative of what actual light is, because it's completely random in terms of its orientation. So the other type is called longitudinal, right? The longitudinal wave, the vibration is parallel to the direction of propagation. Now this one's a little bit different, right? Because it's a little bit harder to see. That's why I got this slower moving spring. So you can get this center, right? Since the energy is going to travel from me to Riley in this direction, then a longitudinal wave means that the spring is going to vibrate in the same plane, in the same linear direction as Riley and I. In other words, it needs to vibrate this way, right? And so the way I do that is I pull the spring backwards and let go, right? You see that wave pulse? You get a similar wave pulse, right, that is decaying because of the table. So we add some tension to this, get it to travel a little bit better. Pull it back, let go, right? The spring is vibrating this way. This local piece of spring is vibrating this way, which is sending wave pulses down through the system. Right? This is a longitudinal wave. Longitudinal, also known as a compression wave, which you may want to write that underneath your longitudinal wave. In a second.
How do you spell that?
Compression. C-O-M-P-R-E-S-S-I-O-N. Longitudinal waves are also known as compression waves. This is because inside of the medium, we are actually compressing part of it together, right? Pressure is the key there, right? Since a medium wants to be at equilibrium, compressing this together adds pressure to this section of the spring. So when I let go, that releases that energy then propagates through the system as a wave. Right.
Does the energy like ever actually reach back to where you started?
So for example,
Because you kind of see it
if
die.
there was no friction, we are going to assume that it would actually last for a really long time. So if I did this up here, right, it's much harder to see up here. but I'm squeezing it together, right, causing a compression, then I let go. A wave propagates through there. In an ideal situation, that wave would echo off of both ends indefinitely forever, right? We know that this doesn't actually happen because in the real world, if this were to happen, my voice would never go away. So everything, every single sound that was ever made in this room would still be echoing off the walls.
That's so.
Right, it's
So why
crazy
does
to
it
think.
not do that?
Because of the fact that the air itself absorbs some of the energy. Because you can imagine this is touching the table, right? Well, this is touching the air. And so for the exact same reason, energy is moved into the air and absorbed over time, and the wave itself decreases, right? So that's kind of what we're showing here. Now the example of longitudinal waves are sound, right? And they are a compression wave in exactly this sense. And it's really easy to picture if you've ever seen a big speaker, because a big speaker moves this way in order to generate the sound. It's literally compressing the air in front of it in order to send a signal out through the air so that you can hear the sounds, right? Does that make sense? So those two waves, although they are different in terms of the way the vibration acts, are essentially the same in every other way. The spring, okay, I'll put this back out like that. The spring moves with a vibration over a short localized distance. If it's moving transversely, then the amplitude is how far it moves from the equilibrium position this way or that way. This is a symmetrical pattern defined by the equilibrium position being the state of no forces or balanced forces, net force of 0 in the middle, right? So we have an amplitude this way, we would call positive A. We would have an amplitude this way, we would call negative A. This is symmetrical, and you can see that as it travels down the system. In terms of the vibration of a longitudinal wave, the amplitude is actually measured longitudinally. So you can think about this piece of spring is actually vibrating over some positive A and some negative A this way. That make sense? The difference, of course, is which direction it's vibrating, whether or not it's vibrating left to right or forward and back.
Is there like a negative direction you can go?
Yes, because we would define the equilibrium position wherever it is as
As
0.
zero.
And so if it moves forward, then we call it positive, and if it moves backwards, we call it negative. If it moves left, we call it positive, and if it moves
back,
right.
it's negative.
Well, so what you have to remember is that we're not talking about the energy. We're talking about the piece of spring vibrating. Because this piece of spring doesn't move to you, right? That was the point of putting the post-it on the spring yesterday, right? All this piece of spring does is move between A and negative A, vibrating back and forth in order to send wave pulses down the system, right? Does that make sense? So what we've looked at so far are what we would call a wave pulse. This is an individual input of energy, right, that we watch propagate through the system. What we're going to spend a lot of time on is continuous input waves, which is what you see on this second graph, right? And so if I input a continuous input wave, that's like multiple wave pulses, one right after another, right? So instead of doing this, right, we're going to do this. And what you have to remember, right, is that that's actually many waves being input through the spring, propagating from Riley to I, and then actually bouncing off of Riley and coming back down this direction continuously. It is weird, but what's interesting is that if you do it just right, right, let's tighten this up just a little bit, but if you do this just right, then you can get patterns that seem to persist, right? See that?
And it looks like it's moving, but it's just staying in the same place.
Right. Because the energy is moving, but the spring is vibrating.
So the energy is going like between it like that, but then.
But the actual spring is only moving left to right.
So are we gonna be measuring the spring or the?
Exactly. So the neat thing about this, right, is that once you establish a continuous input wave, if the system matches up to the particular wave that's input, then what you get is that pattern right? You get that standing wave pattern. So what this is, right, let's see if I go a little slower. I wish this table was the right length. You see how we have two major amplitudes, and then right in front of Audrey, the spring is only moving back and forth a little bit,
Yeah.
right? The reality is that that looks like one wave pulse, right? It looks just like that picture over there, except for the fact that I'm continuously inputting, so there's actually many waves going through this system.
So each time you do this, it's putting in the
Exactly, right? And so every time I move my hand, I'm actually putting waves down through there. And we saw that because if I don't move and I put one, right, that's the wave. But if I do it consistently at a nice constant pace, occasionally I get a nice standing wave pattern. What's great about that is that the standing wave pattern exactly matches each individual wave pulse.
So each one's the same?
So they're all the
Just add them
same.
all up.
So all we have to do is measure the spring, and then we can determine characteristics that actually explain one wave in comparison to the many waves that are all going through there.
I want them the same.
They are the same, that's the point.
So you only need one.
Well, so what's hard is measuring this, right? That's actually pretty hard. But once you have an established pattern, it's actually pretty easy to mark where the peaks and valleys are and actually measure it and get a much more substantial data set, right? That's what you're going to do in the lab
Wait,
tomorrow.
can you do it with like this one?
It would work that way also, but we would need the table to be gone, right? That's like up here. So if I did it up here, right, if I do one single wave pulse, then I get a wave that vibrates. But if I do a continuous input, right, then I can get a pattern that actually matches what an individual wave pulse would be. Right? And so that's really valuable in terms of measurement. And so what's important to recognize is that things like sound and light are not a single wave pulse, right? When you talk, there is actually a sizable amount of vibrations that come out. It's not just one individual vibration, right? And think about it like singing. When you sing, right, you hold a note for a longer period of time. That's not just this, right? That is your vocal cords going like this continuously with exactly the same vibration for exactly the same time frame so that the same note comes out the whole time, right? And then when you change the frequency, right, you actually change the vibrational rate, you get a different pattern. So if I go faster, I get a different pattern. If I go slower, I get a different pattern. And each one of those relates to a different wave, which relates to a different sound.
Wait, what about?
And the same thing is analogous in terms of light. Right.
You know how you see in like movies, like people sitting like really high and then break glass?
Yes,
Are those their waves?
exactly. If we input a wave at a continuous value and it matches the natural frequency of the system, as we keep doing that, the peaks get higher. That peak can then resonate on the glass, which causes the glass to vibrate and eventually break. Those are kind of the things that we're going to continue to be, yes. Those are the things we're going to continue to be studying over the next few days. What your first task is going to be is wave velocity, which is just wave speed. Wave velocity is the speed of energy propagation in a given direction. And I talked to you a little bit yesterday about the fact that a uniform medium, which is these springs, which is air, which is any consistent medium itself, the speed is constant. And that's really useful because that means that the speed can be calculated by distance divided by time, right? And so tomorrow, what you're going to be doing first is doing single wave pulses and timing how long it takes to go down and come back, and doing distance divided by time. If you lessen the tension, then this wave will go relatively slow and you'll be able to see it, right? So this spring has a much higher tension in it and moves much faster. But the underlying premise is constant velocity, which is something that we did second week of school, V equals d over t, right? So the only thing you have to recognize is that since this is a continuous pattern, the wave pulses, V equals d over t is pretty obvious. But when you're doing a wave like this, since you can't see the thing moving, right? We can't actually see the thing moving. We instead need to be able to measure characteristics that make sense so that we can calculate wave speed. That's where changing displacement in the V equals d over t formula to wavelength becomes valuable, right? The distance that a wave travels in a specific time frame is called wavelength. We talked about this yesterday. The time it takes for it to travel that distance is called period, right? So that is the distance of one isolated cycle, wavelength. And then period would be the time that that takes. So you can calculate wave speed or wave velocity by doing wavelength divided by period. And those two things relate exactly to d over t. But what's also valuable is that a lot of times it's much easier, instead of saying how often, or excuse me, instead of saying how long it takes me to move my hand back and forth, right, which would be the period, how long it takes for me to move my hand back and forth. Instead, we would count how many times I move my hand back and forth. That's the frequency. Period and frequency are inverses, so I can change the formula to be velocity is wavelength times frequency. And so it can be either one depending on which variable you're given, and you can convert between the two. Something we mentioned yesterday is that period, right, is measured in seconds. If you did not write that down in the notes from yesterday, please make sure you put that, your units. And then I wanted to add, to make sure, right, in your t equals 1 over f and f equals 1 over t section, period is measured in seconds, which is our SI unit of time. Frequency is the inverse of period. So the unit is something a little bit different that we haven't seen before, which would be the inverse of time, right? The inverse of time, right, in terms of units, period is in seconds, and frequency is in 1 over seconds, which is the inverse of time. 1 over seconds has its own name. This is called a hertz, H-E-R-T-Z, hertz. This is abbreviated capital H, lowercase z. That is the unit of frequency. However, I assume that you have heard this term before, you just didn't know it, right?
Is there a car in that?
There is a Hertz rental car company. I believe that is,
Oh, Hertz.
actually, it might actually be spelled the same, I'm not sure.
It's H-E-R-T-Z-E.
Oh yeah, so there's an E on it. But either way, where you have heard it, I think, is with Wi-Fi, right? And the internet. If you've heard anything that had a certain amount of megahertz, kilohertz, right? Have you heard those terms? No?
No.
Those are the frequencies of the Wi-Fi radio waves that come out of the router, right? That is actually the wave, the frequency of the light waves being used by those particular devices.